Hi everybody, welcome back. So I want to include this last section from chapter 8. So we're going back to chapter 8, and I almost didn't bother dealing with this, but I wanted to do this because for those of you who will be studying some physics later on, and also to show we had another application for trigonometry in real life. Because remember, the trigonometry is all about, leads us to functions that are periodic and cyclic. And we use periodic functions to help model things that are cyclic, that come in cycles. And one example would be simple harmonic motion. That is, we have, if two examples of this is, if we take a spring, put a weight on a spring and we pull this back and then let it bounce back and forth, and ignore air resistance so that this bounces up and down forever. That's an example of simple harmonic motion. Another example is if we have a pendulum and we pull it back and we release it, and once again pretending there's no air resistance, so this will just go back and forth forever. Then this position can be modeled by position of this object can be modeled with simple harmonic motion. So basically, what that involves is we take an object is at rest and we set it in motion, and it just goes back and forth in some way, and its displacement from the initial position or from its rest position is modeled by something we call simple harmonic motion. So basically what this is, you'll find more about this in physics class or a class on differential equations. With the displacement of this object is modeled by this equation where the acceleration is directly proportional to the displacement from the object's rest position. Okay, so we have A equals negative kd, where k is a positive constant. Again, you'll see this in differential equations. You'll see this in physics. So I won't be going over this now. But what this turns, when the smoke clears, what it means is that this displacement can be modeled by an equation of one of these two types, where d of t, if d of t is the displacement at time t, then d of t is either in the form of a times the cosine of omega t or a times the sine of omega t. And again, where a and w are positive constants, the displacement, the difference between displacement and distance is that displacement can be negative or positive as well as positive. So that's why why that's important. Why? Because of course the cosine and sine can be negative and positive at different points, right? So with all this said, though, if we just consider this as a trig function, we already know that A will be the amplitude, and omega relates to the period. Okay, omega, the period of this function. If you graph this function, this period will be 2 pi divided by omega. And the amplitude is the absolute value of A, and in this case that represents the maximum distance the object is from its rest position. Okay. And in addition to this, the frequency, we can think of the frequency as just the number of oscillations per unit time. So it's the number of cycles for a given period of time. And in this case, the frequency is always 1 over the period, which in this case is omega divided by 2 pi. All right. So there's not a whole lot new in this lesson. It's just that we have these functions, which are functions of t now instead of x, and they actually represent the displacement of an object. So just give you a few examples here, just to put this together. So in this first example, an object is attached to a string and pulled down 4 inches from its rest position and then released at time t equals 0. And the time of one oscillation is 2 seconds. Find d of t. what we're to get, this is a very unrealistic situation where we're ignoring air resistance. We do that, but we see that because we're pulling it down, this displacement is going to be negative when it begins. Okay, we're pulling this down, and at t equals 0, we're letting it go. So we can see that d is going to be -4 when t equals 0, and the period, see, the period is 2 seconds. Okay, we have to be a little careful of our units here too. The distance, of course, is going to be in inches. Okay, so we can see that this spring is going to be bouncing up and down. It's going to be always within 4 inches of its rest position. So the amplitude is 4. Okay, and that's really enough. All we need. The period is 2 pi divided by omega. So we said this is the formula for the period. This is equal to 2. If we want, we can cross multiply. We get pi is equal to omega. So that means that d of t is going to be, it should be -4 times the cosine of pi t. Okay, and the reason for that is we want the initial, if we use sine, this will just be 0. Okay, so we want cosine. Okay, and everything, I think, follows from that. Okay, all right. All right, then. For the next trick here, or the next example, here we're already given the formula for this a new object which has a new kind of motion, where its displacement from the rest position is given by 6 sine of 3t, where d in this case is in meters and t is in seconds. So we want to find the maximum displacement from the rest position, the time required for one oscillation, and the frequency. All right, so what's going on in this case when t equals 0, this is going to be 0. So what's going on is, if you were to graph this, here's d and here's t. Okay, what's going on is the function is going to look like this, where the amplitude, of course, is 6. Okay, and then we'll find what the period is. So we're starting at whatever. In this case, we're starting at the rest position, and then the displacement is going positive, then 0, and then negative, and again. All right. So the maximum displacement is going to be 6 meters. Okay, because that's the biggest that the d of t can be, and we can see that the time required, the period, is going to be 2 pi divided by 3. Okay, so that's omega is 3 in this case. So maybe I should somewhere say a equals 6. And omega is 3 here. All right, and so this is in seconds. And what this means, this is approximately, just in case you're curious, this is a little more than 2 seconds. Period is. And then the frequency. So this tells us the time required for one oscillation. That's what the period is. And then the frequency is the reciprocal of this. So this is going to be 1 over 2 pi over 3, okay, which is the same thing as 3 over 2 pi, okay, which is approximately, what did I get, 0.47746, and this is going to be oscillations per second. Okay. But to be more interesting, if we can convert to minutes by multiplying by 60. So if we take 60 times 0.47746, this is going to be 28.6 oscillations per minute. Okay, and when you're doing the homework, just pay attention to what units they want, okay? Or sometimes they'll just ask how many oscillations per second, how many oscillations per minute, something like that. Okay, then another example would be this. Suppose the object on the spring, and I should say the spring is an example 1, is pulled down 6 inches and released at time t equals 0. Okay, you observe 40 oscillations in 1 minute. Find d of t. All right. So let's see. We want to find the equation this time again. I think we can see we're pulling it down, so it's going. So this displacement is going to alternate between 6 and -6. So the amplitude is going to be 6, and that's what A will be. And then the period. Well, what's the period? The period is going to be the reciprocal of the frequency. Now we have 40 oscillations in 1 minute. In 1 minute. Which is the same as 60 seconds. Okay. So we can see that there are going to be 40 oscillations in 60 seconds. Okay. So this is, I mean, 2/3 oscillations per second. And if we take the reciprocal of that, the reciprocal of 1 over 2/3 is 3/2. So this is going to be 1 period. Okay. Maybe I should say 3/2 of a second. Okay. Or 1.5 seconds. Maybe I'll say 0.5 seconds. It was 1 period. Okay, and so then that tells us that 2 pi divided omega is 3/2, and cross multiplying again, we get 4 pi equals 3 omega, divide by 3, and we get 4/3, 4 pi over 3 equals omega. So our distance is going to be, again, when we start, our initial position is -6, right? D is -6 when t equals 0. So this is going to be -6 cosine of 4 pi over 3 times t. Okay, so that should be that. And then one other thing, I'm just putting this as a little addendum. There's something in real life, of course, there's air resistance. Okay, so these things eventually stop moving, and the amplitude just steadily decreases, and things eventually slow to a stop. And that's what the model is going to do. So in reality, the displacement function looks like this. Okay, and there's a lot of the equation, of course, for this gets a lot messier. Okay, the equation that in your book, the equation gives you this equation as to model this. Don't worry about this. Please do not memorize this equation. You'll need it. Maybe you'll need it in physics class if you take physics, but we won't need it here. Okay, but the only thing I'll say is that if A is positive, this e is raised to a negative exponent times t. So it's because of this factor is going to 0, and it's sort of dragging everything else with it. So you have the cosine of something. This is always bounded between 1 and negative 1. A is a positive constant. So this is the factor that it affects everything. And you might see something like this. You might see something as simple as minus e to the minus t times the cosine of, at, or something like that. Okay. This is also going to go to 0. Okay. But again, don't worry about this. Okay. This is a math class. This is not a physics class. And I just wanted to show you that this is damped harmonic motion. This is not simple harmonic motion. This does not satisfy the nice differential equation of acceleration equals constant times displacement. All right. So really, all you're doing right now is just for this topic is if you know how to compute the frequency, the period, the amplitude from those and read those from the equation of the function, you're all set. So that's all I have for you now. Take care.